chapter 9. So hope that everybody had a chance to review the recorded lecture for February, I was 14th. Yeah, 14th. Yeah, 12 and 14. Yeah. So in that lecture, I covered the MOSFET-based differential pair. So chapter 9 talks about two things. One is the differential amplifier. The other one is the multi-stage amplifier. So what the first thing to get really well is a differential amplifier. So for differential amplifier, we have two types of devices. So one is a MOSFET, and then the other one is a BJT. So we're already in the MOSFET. So today we're going to talk about BJT. We're going to have a quiz after the lecture. So let's start with a differential pair. So if you have a master well the contents with MOSFETs, and this is really fairly easy. When we do this, we were going to try to do a few different things. Like initially, for example, we're going to assume beta is infinity, and then we'll look at what happens. And then we're going to remove the beta is not infinity, what happens, and look at that kind of stuff. So this circuit, as you can see, this circuit has two N-type BJTs, and one on the right hand, left hand, and one on the right hand. And the two BJTs are kind of head on to each other. And I had one student coming to asking me, okay, what is the difference between differential pair and a current mirror? So a current mirror is back to back. Their base is connected. For differential pair, the base is outwards. Yeah. So the base, eventually, each is going to connect to an input. Or you connect input between these two terminals. So we'll see that, why we call it differential. So when you have this connected, each has an input. So and then this one is the current source at the bottom. When we do the DC analysis on this one, the first step is we can do a DC analysis on this one. So when you do a DC analysis one, you have a current over here. This is the current source. Now this is ideal current source right here. But in fact, from chapter 8, we already know that we can build a current source, use all kinds of devices. BJTs, MOSFETs, we can do, we can build current mirrors. So this current source provides a DC current, which means each of these are going to conduct some DC current. As long as this DC current is provided sufficient, each of these BJT is going to at its linear mode, linear operation. Okay. Do you still remember what the linear operation means for BJTs? Well, first of all, we know that the voltage from here to here for DC has to be larger than 0.7 volts. And secondly, the voltage from here to here has to be more than 0.3. Right? So those two conditions make sure that this is in saturation, this is in active mode. And if these two BJTs are identical, or sometimes they call them matched, how much DC current will conduct in each BJT? If the two devices are matched, exactly the same. It's a half, right? Because the total current is here, so each of them will conduct half current, right? Half current. And as we said, we make sure this is in active mode. And the voltage, DC voltage from here to here has to be 0.7. But you might say, okay, how can you get the 0.7? Well, because this arrow means the bottom is a voltage source. So this is a negative something, 5, 10, 15 volt, negative. So this is negative, and this is some voltage drop. So this is like, if this is AC signal, for DC, this is short circuit, so this is ground. And this will be minus 0.7 volts. That's for DC, minus 0.7, okay? And, okay, so at this point, this amplifier looks like, what type of amplifier would you define? Is it a common base, is it a common collector, or is it common like a source, right? I mean, common emitter. So everybody says common emitter, which is correct. However, there's a caveat. There's a caveat. There's a DC source over here. For DC, when we do superposition, when we do AC small signal analysis, the DC signal becomes an open circuit. So in theory, this is not strictly a common emitter amplifier because there's a DC source over here. However, we can assume this is going to be common emitter. Well, the reason because if this is open, if this is a standalone, amplifier, you're going to have trouble. Let me draw the half circuit next to this, and you understand what I'm talking about. So if this is a half circuit, you see, if you open this one, this BJT becomes an unstable circuit because the emitter is not connected to anything. This will not work. So this is not a common emitter. But remember, the current source, if it's not an ideal current source, we always have an output resistance in the sense that we call it RO. So in that case, if you open this one, you will have a bypass RO, which is a very big resistor, and the emitter. And therefore, this is not a common emitter amplifier because there's a resistor at the emitter, right? Okay. Now, how do you make this a common emitter amplifier a real common emitter? One of the things you can do is to add a capacitor over here. And the capacitor becomes a short circuit for AC high frequency signal. So therefore, this emitter will be connected to ground. Okay, so that becomes a common emitter. So what we are doing here is we want to look at what does this pair would do. Why would you put these two in, head on to each other? What are you doing here? Well, the idea is to amplify. Eventually, you understand a differential output, a differential input. Okay, so let's look at here. So this we're doing a DC analysis on this circuit. So initially we do DC, like what you guys already said. This is I, and this is half I each, and this is 0, and this will be minus 0.7. And the up there is going to be whatever that voltage VCC minus the voltage drop on that RC will give you the voltage at the collector of each transistor. So now what we're going to do is the first step, instead of doing differential input, we do a so-called common mode input. So this is an interesting name. I don't know somebody who gave it the name, but it makes sense. Common mode means same thing. So if you guys have something in common, right? That means you guys have the same, you're doing something that's the same. That's why it's called a common mode. So when you say common mode, we mean that the voltage over here and the voltage over here is exactly the same. So it's called a common mode. And in a little bit, we're going to apply a differential mode. A differential mode means they're different. The different means the voltage over here is going to be different from the voltage over here. So that's called a differential mode. So we're going to start with common mode. So with common mode, we're going to apply a voltage at the base of each BJT, the same voltage, VCM, same VCM, same VCM. So now, if this is VCM, how much is voltage over here? If the base is VCM, the emitter is VCM minus 0.7, exactly. Here's the voltage here is 0.7. So all this voltage plus 0.7 will get VCM. So VCM minus 0.7 we'll get the voltage over here. Okay, so we get the voltage over here. And then what is the voltage at each of the collector? We're going to say VC1. Let's look at VC1. VC1 is going to be VCC minus 1/2 alpha times I times RC. Okay, you might say, why alpha? Can anybody tell me why there's alpha here? Why not just I? When you get VC1, we say VCC minus current times RC gives you voltage at the collector. Why we use alpha times I, not just I? Well, because the current over here is emitter current. What's the relation between emitter current and collector current? It's alpha. So if I want to refresh you guys, is that IC is equal to beta times IB, and IE equal to IC plus IB equal to 1 plus beta times IB. So IC equal to IE over beta. That's what happens. And beta equal to alpha plus 1. That's why we have alpha. Okay, see, not so important, but just give you the idea. So what happens with 1/2 alpha? Okay, that's what you get. So now we got the two output, VC1 and VC2. Because I is identical, alpha, everything's identical. The two transistors are matched. So you would immediately say, well, the VC1 and VC2 are going to be the same. Right? The two equations are identical. The I is identical, everything identical. So, and then we want to measure the difference between the two collectors. What would you get? By definition, VO is VC2 minus VC1. Because VC2 and VC1 are the same, we get 0. The voltage is 0. So it becomes very simple. You say, okay, well, you get a transistor, you apply voltage at the base, and then you have the current source to bias the transistor. But eventually you get the two outputs that we see, then you measure this two, you get a 0. So what's the point? Well, because this circuit is not designed to amplify a common mode input. Common mode input means that they're different. So think about it. If VCM1 is different from VCM2, what would you get? Would you still get a 0? No, you're no longer going to get a 0, because what happened is that if VCM1 and VCM2 are different, and the current is no longer going to be 1/2 anymore. Okay, how much it's going to be, we're going to look at later. But if these two are not going to be the same, it's not going to be 1 I over 2, and then VC1 and VC2 are going to be different. Because VCC is the same, alpha is the same, RC is the same, but I is different for each one. Therefore, this VO will not be 0. So then that's why we'll get into the next step is a differential amplifier. Okay, we're going to get to that point. Oh, by the way, we have this example here. So the example says we have 1 volt input, and this will be 1 minus 0.7, 0.3. And if we know the current, if we know alpha, we basically can calculate the output in at VC1 anyway. So that's we're not going to do too much on that. So, oh, okay, yeah, no, actually, I'm wrong. So here, what it says here is that if we connect this to ground, and this is 1 volt, that's what I said earlier. You can ground this to 1 volt, and this is 0.3, because this is 1, and this is conducting, this is 0.3. If this is 0.3, this is ground, what happens? This one is off. If this one is off, and then all the current is going to connect on this one. So therefore,
you have VC2. Okay, let me write down here. So then you will have, so in the case here, so how much is VC2 now? See, VC2 is VCC minus alpha I divided by 2 over there, but really that equation is no longer valid. So it's going to be VCC minus I2 times RC, but I2 is 0. So equal to VCC, I don't know how many, 10 volts, whatever. Let's call it 10 volts. So VC2 equal 10 volts. And how much is VC1? So VC1 is going to VCC minus I1 times RC. So I don't know the RC value, so I cannot get it. But in any case, so your VO is going to be VC2 minus VC1. It's going to be I1, which in this case is I times RC. So this is your solution. Okay. But what happens if you, oops. Oops. Those are not good. I have to learn new technology. Okay. So yeah. So this one says that if you do again, if you do this one, you will get this. But then if you apply minus 1 volt instead of 1, see now what happens? But of course you might say, okay, how do you know this is off and then this is off? Well, you can always do some assumption, and then to later reach own assumption. For example, if I assume this is still on, how much voltage will be here? If I assume this is on, this is minus 1, minus 0.7, this becomes minus 1.7. If this is minus 1.7, this is 0. What happened to this one? This will be on. So if this is on, this cannot be 1.7, it has to be 0.7, which means if this is 0, this has to be minus 0.7. If this is minus 0.7, this is minus 1, the difference is only 0.3, this one will be off. That's why this is off, this is on. Okay. So we got the voltage over here. That's what you get. And so that's two extreme examples, is like 1 volt. But what happens if I apply like a small signal, very small, but it's different, but it's not enough to turn any MOSFET on. Just a small difference. That's what happens here. So I ground this one, but instead of putting minus 1 or 1, I put just a small signal, very small. But that small difference is not going to turn off this transistor, but it's going to shift the current a little bit. So this one becomes 1/2 I plus delta I, and this one becomes 1 I over 2 minus I. The reason this is a little higher because you have a small value. See, remember, the current is always the current like IC. Remember what happens to IC? IC is IS times e to the power VB over VT. So if that VB is slightly higher, so IC will be slightly more. But if VB increase so much, the IC will shift to one side. But if it's just like 0.7, like a 0.1 or 0. Maybe 2 even, okay, that'll work. So so then the equation we can write is VC2 will be VCC minus I2 times RC. Well, this I2 becomes I over 2 minus delta I. Delta I is the difference, that's cost.
times alpha. And VC1 becomes VCC minus I1 times RC, well, I1 equal to 1/2 I minus plus delta I times alpha. So plugging all these equations, then you will get VO equal to VC2 minus VC1, and this equal to 2 times alpha, delta I times RC. So this is the final answer. So if you have a small value at one gate and one base, but the other one is grounded, you get an output that's related to the change of delta I. Now, how much is delta I? It depends on how much this difference is going to be. But how much difference we can calculate? We can calculate use this equation over there, top there. So we can calculate. Okay. So that's why we can have that. So this is another example that has this PMOS instead of NMOS. So with PMOS, you can look at this. All right. So we can do a similar analysis. So suppose you have minus 5 volts over here. We want to find out what is VC1 and what is VC2. And we have one like gate grounded and the other one connect to 0.5. Now, if this is 0.7, if this is 0.7 or more, you will know that this will be something like a, well, we have to figure out which one is going to be conducting. So let's start with something like 1 volt instead. So we can assume, so this will be fair because I don't know which one is on. So we can assume Q1 is on. So if we assume Q1 is on, what voltage would you get at V1 here? How much would be V1? 1.7. Okay. So if V1 is 1.7, what happened to Q2? What happened to Q2 now? See, V1 is 1.7, but the base is grounded. So V2, Q2 has to be on. So must be on. So if Q2 is on, but if Q2 is on, we have a problem. If Q2 is on, how much is V1? 0.7. If we want 0.7, how about Q1? So Q1 from base to emitter, you only have 0.3 volts. So that has to be off. So that's why Q1 is off. That's we start with by assuming Q1 is on, and then we find, oh, that's wrong. It cannot happen. So that's why. So Q1 is off. So that's for V1 equal for V like VQ1 or VB1 equal to 1 volt. But in this case, in this example, they have VB1 is not 1 but 0.5. So if VB1 is 0.5 volts, so most likely both can be on. Like let's assume like this 0.5. Okay, let's erase this now. That's it. So for VB1 0.5, we can do the same thing. We can assume Q1 is on, and then we have V1. Again, we have V1 here. V1 will be 0.5 plus 0.7. It gives 1.2 volts. So this way that you know that Q2 it has a problem. Because Q2 from base to emitter cannot have 1.2 volts. So same thing,
then we will find out actually Q2 is on, but Q1 is VB1, VBE1 is only 0.7 minus 0.5 equal to 0.2 volts, which means Q1 is off. So when the voltage is kind of large, so this sense can only be one is on, the other is off. If that VB1, this VBE, the difference is small, then you can have both on, but the current is shifted from one to another. Okay. Okay. So now what we're going to do is we're going to start with a differential input. So this is the circuit. Forget about the equations on the diagram. Only look at the circuit itself. So only look at the circuit itself. Everything else was the same from the common mode, but instead we apply an input over here. And the input over here, the positive will connect to Q1, and the negative is connect to Q2. So that's you apply a voltage on both sides. Because now you don't have a ground. Now, so there are a couple ways to do this circuit analysis. One way is to add a ground over here, or over here, because this is a voltage source. I mean, naturally you say, okay, I can ground the voltage source. If you ground the voltage source, this circuit becomes which one? If you ground the voltage source, which means this one has an input, this one has zero input, grounded. So this will become the circuit we analyzed earlier, like this one here. Like you have a small input, but this is grounded. Okay, so we already analyzed the circuit, we get output like this. So we don't do that again. We only continue with. So the other way to do this is to divide this into two. Like this is one voltage, right? But we're gonna divide the voltage into two voltage source. So what we're doing is here, we divide this one into two voltage. They're both AC. Then we ground in the middle. So this, again, could be done in real life. You just simply ground the middle. If you can't separate, divide the voltage into two. Or for the convenience of analysis, like mathematical calculation, we make a virtual ground. So, okay, let's assume this, we can divide this, we make this middle a ground. So if we make this a middle ground, so this is 1/2 and this is 1/2. Okay, so then we're gonna move this one, we're gonna leave it here, but we're gonna move this one all the way to this side. See what happens? I'm gonna like erase this one, just make it like a look easier. Okay, so we're gonna leave this one voltage, but this becomes 1/2 VID. And then the other one, we're gonna move it here. But this one is gonna be plus, minus, remember this here, because this is the ground. All this is become the ground. So this is minus. Okay, so the symbol here, they call VID, I is input, D is differential. The previous one called VCM means common mode CM. So we have 1/2 VID on the left hand, we have 1/2 minus VID on the other side. So if you look at this, you say, well, we now have the VBE, because this is like a common to both, right? So this VBE over here becomes the DC VBE plus 1/2 VID. But this one becomes VBE, which is the DC bias voltage minus 1/2 VID. Okay, so you would naturally know that the current over here is going to be a little bit more than the current flowing on this side. So the current is more on this side, the more is less on this side. And then, but you're still saying, okay, how much is the difference? Like, how would I know? Like, how do I calculate this? So forget about the equation for now. This is where we have to get into the small signal model. Okay, so suppose what I need to do is I'm going to add like a, so I'm going to need to draw the small signal circuit so that we can get the actual output and input differences. So because you might also say, well, can you do the analysis on here? Yes, we can, because from this VB to here, we can calculate IC. Because IC is, again, IS times e to the square VB over something. And it's this one too. So getting the difference, and you can get the voltage, and eventually you can get the difference. But that process are going to give you the same result like this one, but it's much more complex. So instead, we know that VID is a small signal, so we can draw the small signal equivalent circuit. So that's what we're going to do. So we're going to draw Q1 and Q2. We're going to draw one by one. So let me erase this so that gives me more space. So for Q1, let's draw the circuit like this. So for Q1, we have the GM V pi 1, and this is here. Okay, so we got a Q1 equivalent circuit. Over here, well, you could also draw RO, but I mean, this is something that we will add later on, but we can neglect it for now eventually. And on this side, so now look at what is connected to the base of Q1. It's the 1/2 VID, right? And what is the collector connected? IC, right? RC, right? Okay. So here we're going to have VC1. That's your output. Okay. So now let's look at so for now the emitter we can leave with emitter for now because the emitter is actually connected to the current source. I mean, for DC, that's an open circuit. For DC, it's open. So we don't have to draw. So you might say, okay, the emitter is not connected to anything. No, yes, no. But we're going to draw Q2, and then you will see why it's okay. So for Q2, we're going to start from the other side. So okay. So that's Q2. So this is RO2. This is GM2 times R pi 2. And this is B2. Okay, so now look at the Q. This is Q1 and this is Q2. Now look at the Q2. What is connected to the base? So remember earlier base, we moved this one to here. Remember, this is 1/2 minus 1/2 VID. So now we can connect 1/2 VID minus 1/2 VID. Okay, so that's the base. You see the way that we draw this is we flip because the transistor is like that. Okay.
then this is the VC2. The VC2 over here, VC1 over here. Okay, so for the emitter, now it's important. For the emitter, see what happens? For the emitter Q1 and the emitter Q2, they're connected, right? Oh, so they're connected. Okay, then we just simply connect them. We'll connect them. So this connection is actually important because if they're not connected, this two circuit actually will be like two separate circuit. Okay, so it's very hard. But once they're connected, you see, I know many of you like to draw like a closed loop circuit. You see what happens? The ground can be connected. You see now what happens? There's one half VID and one half VID here. That's really looks like here. Okay, yeah. So we get that. So now you can see. Let's do this together. So, what is V pi 1? How much is V pi 1 from the circuit? Well, it's a little bit tricky at this point. You say, okay, well, this is the ground, but that's not a ground. But in fact, because this circuit is symmetrical, in fact, if you do analysis, eventually you will find that the middle line over there is actually equivalent to ground. So it doesn't look like ground in this case when you draw the circuit, but in fact, this middle part is going to be a ground actually. So if that is a ground, I mean, that's like a virtual ground. It's not exactly ground. You cannot see, there's no physical ground. It's not physical ground, but it's the virtual ground because that voltage is 0. The reason is that this circuit is symmetrical. If you look at the circuit is symmetrical and it's 0, but of course, if we do this eventual mathematical equation, we'll get 0. But for now, you have to accept what I said. But later on, if you want really to understand it, you'll be able to derive the math equation. You'll find actually there it is 0. So if it's 0, which means everything here is 0. Like everything here is 0, right? So everything here is 0. So everything here is 0. Now you can tell me. So V pi 1 is going to be VID over 2. And V pi 2 is going to be minus VID over 2. Okay. So then let's look at what is the VC1? VC1 is going to GM1 times V pi 1 times that resistance in parallel, which is RO1 in parallel with RC. And then we'll also have don't forget the negative sign. And VC2 equal to minus GM2 V pi 2 times RO2 in parallel with RC. And how much is VO? VO is the difference between VC2 and VC1. So now you plug all this in, you will get so you'll get the equation, you can put them together. But if we want to simplify this one, we need to do some assumption. Like in this case, yes, right. From collector to ground, yeah. Great, but initially it was connected to ground, yes. Well, you're right. So initially, okay, I think you had a very good observation. Is initially, you're right, I probably made a mistake here. So initially, this is connected to, so this is connected to ground, and this is connected to ground. Yeah, you are right. But eventually, since later on we'll find everything over there is ground, so we'll just simply connect everything like this to a ground. Yeah, because it is a virtual ground. It's not a physical. You're right. So it's a little bit difference between physical ground and a virtual ground. A virtual ground is by mathematical calculation, the potential is 0, but it's not actually physically connected to the ground. Okay, so but we do some assumptions here. So we're going to assume that GM1 is equal to GM2
equal to GM, and RO1 equal to RO2 is equal to RO. And then RC, of course, is the same. And also, V pi 1, we know that it's 1/2 VID. The other is positive 1/2 VID. So if the both sides has the same input, this two will cancel, we get a 0. But now since one is positive, one is negative, so we got, when you plug this in here, you plug in this one here, you'll get the second term is becomes negative, positive, and the VC1 becomes negative. So over here, you have really GM times VID times RO divide, not divide, but parallel with RC. Okay, so this is the final result you get. And then if we want to get the gain, like we call the differential gain, we gain is the division between the ratio between input and output. So gain, let's call it A. So A is equal to VO or VID. It becomes GM times RO in parallel with RC. Okay. So this is how we get our output, and we also get our gain. Okay. So in the book, okay. And then in the book, it does this, instead of doing the pi model, it started using this T model. And if you remember, T model simply have the RE over here and then alpha times the IE over here. So this is the base input and this is the base. So they have input connect to this, the differential input connect here. And then this model is a little bit easier than the other. I mean, the other one is not that difficult. Just this one is even more straightforward. And you can calculate, eventually get your output, which is right. See here is VC2, this is VC1, and your VO is VC2 minus V. This VO is VC2 minus VC1. You got alpha and RE instead of GM, you know, which is okay. These variables can always be connect to each other or convert to each other. And this one says that, well, if there's a resistor at the emitter, so when this happens is, this doesn't really happen very often in IC design, but in some cases, they do have this resistor at the emitter. So this becomes no longer a strict common emitter amplifier. This becomes sort of between a common emitter and a common collector. So it has some of the properties of common emitter and some properties of common collector. And it does give you, like, you can draw the, and you can draw the equivalent circuit. If we draw the pi model, and we can find that eventually that like this resistance, in fact, can be eliminated. The reason is that the current over here and the current over here, it becomes, well, if I go back to one of the circuit, I think it will be a little bit clear. Yeah. So in this case, if you use the T model, you see there's RE, which is this is the internal resistance of the RE. But if you get this RE here, which means there's a resistor at the emitter with the T model. So if there's resistor at the emitter, it's better to use the T model. If you use the T model, simply what happened instead of this single R lowercase e, you add another resistance, like a capital RE. So that's what happens over here. You get RE. So instead, you can draw the circuit. So I can draw the circuit. Yeah, so they didn't draw the equivalent circuit over here, but I can possibly draw the circuit. Is So instead, you will be simply drawing RC for a current source. You see current source, and then yeah, and this RE, this RE. And you draw the same thing on this side. I think they're going to be connected. Yeah. And your input is at over here. So that's all. So what you're doing is you really add this RE onto that lowercase RE, and then that equivalent circuit will become available. But what happens is that you will find out that this REE, in this case, in this example, we have REE over here. Like remember the previous circuit we had the current source. Remember we have current source, and when I said the current source, the DC current source is an open circuit for AC signal, right? So if it's the current source for open circuit signal, so what happens that this circuit will not work. So I add RO on the side, right? So this is kind of the RO of that current source. So if you purely look at this circuit, there are some problems. There are some problems. Do you see that the top, they didn't connect to VCC, they connect to ground. Why? So if you have to read this, this says this equivalent circuits only applies for differential put signals. It's not displaying the DC. Okay, so this is actually a small signal model, but they didn't draw the small signal. They leave the BJT in place just to show how it works for small signal. Now, let me ask you one question here. If I replace the top to ground with VCC, now suppose like I replace this one with VCC. Is that okay? Is this amplifier going to work? No bias. What do you mean no bias? Yeah. So this is the ground, and we know this is small. So if this is small and this is ground, whatever this current is going to be, this is going to be above ground. And this is above ground, this is small. Let's say this is 0.1, and this is 0. Would this be in active mode? No. So it's not going to work, right? Even if we did it, we see it doesn't work. So how do you make this work then? You change this to like a minus V. So if you do that, this will work. Now, of course, this DC voltage source becomes a ground in AC signal. So that's why this particular example, they actually draw the signal like this. So in this case, I mean, you can even think about there's a current source over here, right? So this is something like, and this RE becomes the RO of that DC current source. But the problem, of course, is that because this RE, so I need to go back to 1 second so that I don't have to draw the equivalent circuit anymore. So I want to look at it here. In this equivalent circuit, if I have a REE connected in parallel with the current source, where would it be that REE in my circuit, in my equivalent circuit? Where would I show the REE? Well, if I have to show the REE, which is here, well, no, actually, let me, this is, So this RE is between this one and the emitter of this one. And let me just a little bit better picture. Between the emitter of this one, and then let me also, oops. Let me erase this. So this is REE to ground. And then this is ground, and then this is ground. So what happens that this REE is over here. And you see that RE on top, they're all connected. At the bottom, they're all connected. Would you expect any current going this way? So this current over here at RE is 0 for the AC. So if the current is 0, which means we really don't care. So we got to eliminate it. That's why in this slide, I want to say, okay, that RE got eliminated. So this eliminated, this becomes this circuit here. And for this circuit here, in fact, they're actually like connected here, but if they're connected, it's okay. But since they're connected, you know, like earlier I saw the virtual ground, so we basically just typically keep separate. Okay, since they're ground anyway, so we can separate this into two different grounds. Now you can calculate half circuit and half circuit. So that's why we already done that. So this is a half circuit on the side, and you guys already saw it earlier. And yeah, so you know, when you say that this is RC is not connected to the emitter, which in this case, because the emitter is grounded, and this is grounded, so everything here becomes like a loop. And you can draw the other half, which becomes exactly the same. Like you would draw the other half, ground. So this is 1/2 minus 1/2 VIG, and this is VO2. And then your VO is equal to VO2 minus VO1. And this will give you the same result we already derived, so we're not gonna repeat what we have done. Let's go over maybe this one example, and then we will be done for today. Okay. So in this example, they have this, the current is 1 milliamps. So I think what you can do, let me say what it's asking for. You evaluate the following, the input differential resistance ID. Okay, the overall differential, yeah, we probably don't have all the time to do this so much. So what we have in this circuit is the difference of this circuit is that they really added RE here and RE here, and also they added the input resistance of 5 kilo ohms. So in order to do a good job on this one, yeah, we would have to like draw the equivalent circuit, and the easiest way is to draw half circuit and then get the result multiplied by 2 for the output voltage, and for the resistance divide by 2. Okay, so in this case, let's draw the half circuit over Q1. So, oops. Now we're gonna, I'm gonna neglect, actually, sorry. I'm gonna neglect the RO in this case. And the emitter is connected to RE, ground is R pi. and RC is 10 kilo. We can get a wheel. So what the circuit gives you is beta is given. The beta is given is at 100, and also I is given is 1 milli. So in this case, we can get I1 is 1/2. I is equal to for small signal analysis, this current, DC current, we always think they're half on each side. Now, because of the small signal input, it will be slightly more than half. This will be slightly less than half, but so we still treat that DC busing at half. So that's how this current is divided half on here. And then, so in this case, you can calculate R pi. You should be able to calculate R pi. You should be able to calculate GM. And then this is V pi, and this is GM times V pi. So when we calculate all of this, we can do like again, we can do for example, a nodal analysis, or we can do sort of like current combinations. Because if we know this is a current IC and this is a current IB, or this will be beta times IB on the right hand, and this will be 1 plus beta times IB. So and then you can calculate like VE over here. So VE equal to 1 plus beta times IB times RE. So you got VE. Now you have this IB. Now you can calculate IB equal to 1/2 VID divided by 2. That's the voltage, and divided by 5 kilo ohm. That's input plus R pi, and then plus this. No, this one's okay. This is V. Oh, I'm sorry, I made a mistake here. What I meant is 1/2 VID divided by 2 minus VE over 5 kilo ohm plus R pi. This VE. I cannot write on this pen. So, and then you can plug in this IB here, right? And so that you will get, then you can calculate V pi. V pi is IB times R pi. IB times R pi. Okay, V pi no. So now you got VO1 is GM or beta times IB times RC, and then minus sign. So it's just a lot of like mathematics. You have to do it. So I think we're going to stop here so that you guys will have enough time to do the quiz. But I think so for now we know the differential pair. So and we're going to continue to talk about a few more things about the differential pair. And okay.